Okay, great. Thanks a lot, Dana. Uh, Maybe we should wait another minute because not everyone's watch is perfect.
Yeah.
Okay, well, I guess it's time to get started. So, thanks all for coming. I'm Martha Haynes, and uh, this is Imagining the Universe, where we do some weird things and discuss weird things and look at different objects in the universe. So, as was stated, I think, in the little summary of what we were going to do today, we're going to talk about what's up in the night sky. We will then address a question that I overheard someone, and I'm not sure who it was, ask at one of the recent LLH events. And I thought maybe we should actually discuss the answer to it. And then we'll take a look at a couple of images of black holes, because we think that black holes are black, so they have no light, so how can we actually see them? The first thing to talk about, though, is what to be looking for in the sky. The new moon is occurring tonight, and so you can't see the moon. But over the next few nights, if you look towards the west, we should be able to see the crescent moon later in the week. If you look towards the southwest in the evening, you can see Saturn and Venus. If you look at Mars and Jupiter, they're high in the sky through the night. And I hope that some of you have been looking for the constellation of Orion the Hunter and Sirius the Dog Star, which would be down over here. Orion should be directly south around 9:30 in the evening. And maybe it will even be cloudy tonight. Who knows? But as I said, the moon is new tonight. But over the next nights, if you look towards the west southwest in the next few nights, on January 30th, the moon will be just down here. It will be a tiny, tiny crescent. The next night, it will be higher up in the sky and a little bit more filled. And the next night, it will be even higher up in the sky and a little more filled. But you should also be able to see Saturn and Venus. I'll just point out that the next full moon occurs on February 12th, and this full moon is called the snow moon because presumably it occurs in February and it's cold and there's snow. Let me also say that if you have any questions, it's hard for me to see hands if they're raised just by doing this, but I can tell if someone raises a Zoom hand using the reactions button. Okay. There are, as I alluded to before, you can see a lot of the planets in the next month, which is kind of exciting. Mercury is hard to see and because it's lined up with the sun in the next 10 days or so. But it will then become visible in the west, low on the horizon, just after sunset. But in January and February, if you look towards the southwest in the evenings, you can see Venus and Saturn. This is another rendition of the plot that I just showed before. And in fact, if we go, this is January evenings. If we go to February, you'll see Venus also very prominent. Mercury on February 28th will be just visible above the horizon. Maybe we'll come back and revisit this in a month when we have our next session and have everybody try to look for Mercury. Mercury never gets very high above the horizon, so it's hard to find. It's also not very bright, not nearly as bright as Venus. Mars and Jupiter are also visible, as I said, and Saturn is visible close to Venus right now. Okay, so those are things to take a look at. One of the things about Venus in February is that it's really, really bright. And that's because it reaches its peak brightness on February 14th. Maybe Valentine has something to do with that. I don't think so. Venus actually has phases. So let's remember that if here's the Earth and here's the Sun, and the Sun should be much bigger, of course, in this diagram, Venus moves around in an orbit closer to the Sun than the Earth. And what we see when we see a planet is the sunlight reflected off it. And so sometimes we don't see any light from Venus because the lit side, the side that faces the sun, is pointed away from us. And then it will grow and have crescent, half Venus, gibbous like the moon, and it will be full. But when it's full, it's on the other side of the sun from us, so it's smaller than when it's close to us and new. Venus reaches its brightest part about a month before and after it reaches inferior conjunction. That is, when it's not completely full, but it's very close to us. And the next inferior conjunction happens in March, and so it will be bright in February and it will be bright again in March. Okay, another thing that will happen, and we'll talk more about this next month when we're closer to it, is in the month of February this year, particularly on February 28th, there's what we call a planetary alignment. And what that means is that a bunch of planets are above the horizon at the same time. They're not close together on the sky. They're actually quite far apart on the sky. But it turns out on February 28th, all of these planets will be above the horizon. We can't see Uranus, we can't see Neptune without a telescope. Saturn will be very close to the horizon, as will Mercury, but Venus, Jupiter, and Mars will be up there. So we'll come and talk about that in a month. Okay, the next thing that I wanted to talk about was this fact that I overheard someone, and I don't know if anyone remembers saying this, I don't remember who it was, but I remember that someone at one of our events said something to the effect of, have you noticed that the sunset is getting later more than the sunrise is getting earlier? And so here's our diagram that we looked at the last time. This just shows the time of sunrise and sunset throughout the year. Of course, we have this adjustment because we switch from daylight saving to or from daylight savings time. But you all know that the days are shorter in the winter and longer in the summer. But in fact, it is correct that right now in January, sunrise is advancing more, sunset is moving later and later, more than sunrise is moving earlier and earlier. And you can find this out if you ever want to find sunrise, sunset times. You go to timeanddate.com and put in Ithaca, New York, and it tells you everything you could possibly want to know. And the point of this, my actually going there and downloading some numbers, is that in fact, in January in the Northern Hemisphere, the time of sunset changes more, that is, it sets later, more than does the time of sunrise rises earlier. And in fact, between January 23rd and January 31st, according to this diagram, The sunrise occurs 7 minutes earlier on January 31 than it did on January 23rd, but the sunset advances by 11 minutes. And in fact, if we go back and look earlier in the month, it was even more prominent than this. Between January 8th and 16th, the sunrise only changed by 2 minutes, but the sunset advanced by 9 minutes. So, why is that? Well, it turns out that it's a combination of effects. So, let's remember that the sun and the Earth are both moving in some way. In particular, the Earth rotates on its axis once every 24 hours. This is what causes the sun, the stars, and the planets to rise in the east and set in the west. We call that the apparent diurnal motion of the celestial bodies. At the same time, the Earth is revolving around the sun. It does that once every 365 and a quarter days. And this means that different parts of the celestial sphere, the stars, the location of the stars in the sky, are visible at night at different times of the year. And this produces an apparent motion of the sun among the stars, which we call its apparent annual motion. The other thing that happens is that the Earth's spin axis is inclined by 23.5 degrees to the plane of the Earth's orbit around the sun, which is reflected in the sun's apparent path across the sky. And so the sun moves, the sun's apparent path in the sky is not the same in the summer as it is in the winter. So, and another thing that happens is that the Earth's orbit is not circular. So we have this little diagram where we have the Earth revolving around the sun. In July, the northern hemisphere is tilted towards the sun. In January, the northern hemisphere is tilted away from the sun. But because the Earth's orbit is not circular, in fact, the Earth is closer to the sun in January than it is in July. So you might think that it should be warmer in January, but you know that it is not. In fact, the closest approach of the Earth to the sun in its annual orbit was on January 5th. And this is just the superposition of two images of the sun, one taken when the sun was close to the Earth and one taken when the sun was further away from the Earth. And you can see that when it was at aphelion, that's the part where it's furthest from the sun, it would appear a little bit smaller in the sky than at perihelion. So it should be obvious to you that this is not the reason
You should.
why it is cold in the winter and warm in the summer. This is not the cause of the seasons on the Earth. But here's a little diagram. Again, the important point is how the Earth is tilted with respect to the sun. So in the summer, the northern hemisphere tilts towards the sun. In the winter, the northern hemisphere is tilted away. That causes two effects. The first one, and these are diagrams that are supposed to show if you're kind of standing on a spot on the Earth and this is the horizon, and we look at the sun rising in the east, reaching a maximum height at noon, and then setting in the west. In the winter time, the path is shorter and the sun is lower in the sky at noon than in the summertime, when the path is longer and the sun rises higher in the sky. That means that the sun is above the horizon longer, so the daytime is longer. But it also means, if we look at the lower diagram, if you face south and you figure out how high up in the sky is the sun at noontime, this is the winter. The sun is lower in the sky at noon than in summer when it's higher at the sky. And so this is what causes the seasons on the earth. First, the path of the sun in the sky is longer so that the length of the daylight is longer, and the sun, of course, heats up the earth, causing it to be warmer. But the other thing is the concentration of the sun's rays is much less in the winter. They spread out over a bigger area. They appear to be more diffuse. Whereas, as you know, in the summer, the sun feels warmer than it does in the winter because the rays are concentrated on you and the snowman melts. Okay, so back to our concept of why the time difference. And that leads us to the question is, what is a day anyway? Well, astronomers define a day as the time between two successive transits of a celestial object. And what that means is the time between when a celestial object like the sun or a star or a planet is directly south until the next time the object is directly south. When we are talking about a star, we tell time from noon to noon in what we call sidereal time, and that's another problem which we'll talk about in February. What we're interested in today is talking about the solar day. What the noon in a solar day is from the time the sun is at its highest point in the sky till the next time the sun is at that same point or almost that same point in the sky, when it crosses directly south. Then the other thing we have to ask is, okay, fine, we got the definition of a solar day. What is noon? Well, that depends on whether we're telling time by the sun or whether we're telling time by our watches. And therefore, we have to distinguish between what we call civil time, which is an arbitrary time set by agreement when someone says it's noon, and exactly 24 hours according to our watch, it's noon again. But the sun is actually moving in the sky because of all these earth motions and these tilts. And so solar time and civil time turn out not to be the same. Civil time, remember, is just defined as to be a time which is set by international convention. It has exactly the same length. Remember, I said that a year, the time it takes in the Earth to go around the sun is actually 365 and a quarter days, but we decide that a year has exactly 365 days, and a day has exactly 24 hours, each one 12 hours before the transit of the sun and 12 hours after the transit, and then we divide things up into hours and seconds also. Just note that the ancient Egyptians actually tried to divide daytime into 12 hours and nighttime into 12 hours. But that kind of made a problem because since the sun is up for different amounts of time in the summertime than in the wintertime, that meant that the length of an hour varied. And that got very confusing. Okay, that's just a little bit of an aside. Peter has a question.
Yeah, Martha, hi. Just to go back, you were talking about the twilight, and there were some terms that came up. There was astronomical twilight, nautical timelight, and twilight, and
Civil twilight.
civil. There were three. What's the difference between those? Or what do they
Well,
mean? Different.
it's a standard astronomical twilight is the actual time when the first ray of sun, remember, the sun extends over a certain size in the sky. So are you going to call twilight when the first ray reaches Earth, or are you going to call it when the full sun is above the horizon? That, of course, is what we call sunrise. But in fact, some of the rays of the sun start, because of the atmosphere, they start reaching the Earth earlier. And in astronomy, we don't want any confusion. We want no rays to be hitting the Earth. And so astronomical twilight is defined very severely. Nautical and civil twilight have their own definitions, but that's the basic difference.
Okay. All right. Thank
Okay.
you.
Yeah. Okay, back. Okay. So another what's in, so we have this definition of civil day, but civil day is set by our watch. Somebody controls it. Every now and then we have to have a leap year in order to catch up and get the solar and the civil day to be more in line because of the 365 and a quarter day thing. We also sometimes have to add leap seconds, but it's all set by international convention. The sun doesn't care about international convention, it does its own thing. And the solar day has a variable duration due to the fact that the Earth's orbit is circular and the tilt of the Earth's on its axis. And so what we're interested in knowing is the difference between the civil and the solar time. That is, if you start and have a tick counting the number of ticks in civil seconds, and you compare that to, say, a sundial, which is displaying actually where the sun is in the sky, there's a difference between that two, and we call that the equation of time. It's actually very nicely described in the Wikipedia article if you look up equation of time, but I'm going to summarize it very briefly here. Okay, so this is a plot on the right. You see an image, a succession of images taken over the course of a year of the sun in the sky as viewed from a particular location in Turkey. Okay, so this is a picture of a photo of where the sun is exactly at civil noon. And you can see that the sun moves, of course, because of the tilt of the Earth on its axis, but it also moves in time relative to the civil noon. And this is what is called an analemma. So you see it as a photograph on the right-hand side, and you're seeing it as a nice little plot from the Royal Observatory in Greenwich on the left-hand side. And so what we expect is that the solar time advances or becomes less relative to noon because the shape of the Earth's orbit around the sun is not circular but elliptic. What that means is the Earth is moving at different speeds. It moves faster in its orbit near perihelion and slower at aphelion. And therefore, the difference in the time between successive transits of the sun occurs at different orbital configurations. And so we created the civil day because it was more convenient for us for scheduling. But in fact, it is fictitious. The true day should be the solar day. So there are two effects that are taking place. One is the orbital tilt, and one is the effect of the elliptical orbit. In this diagram, and I'll show you a little animation of this in a minute, we can plot over the course of a year the average or the passage of the sun on the meridian as an average through the year. That should sort of correspond to what we think of as our civil noon. But there are two effects that occur that sometimes make the sun's passage of its maximum above the horizon on a given day occur later than the mean sun and sometimes earlier than the mean sun. And you can see that in the analemma. So if this is noon, then sometimes the sun is at noon is earlier, and sometimes it's actually past its peak point. And so maybe this animation will show up. There are these two competing effects, one due to the Earth's orbital eccentricity, and one due to the effect of the tilt, also known as the obliquity, that produces the analemma. And it also tells us how the time of solar noon varies compared to civil time throughout the year. And it happens that we're in a period when the sunset time is advancing faster than the sunrise is moving earlier because of both the fact that in January we're at perihelion and the sun is moving really fast, and the fact that in January in the northern hemisphere, the Earth is tilted away from the sun. So, probably more than you wanted to know. You can go read about it more. As I said, the Wikipedia article is pretty nice. Of course, this has been mathematically derived out, and it's now very accurately timed. Okay, anybody have any questions about that? Okay, then let's go to the second part of my discussion, which is how can we see a black hole? And so I present to you an image of a black hole. And you're supposed to be terribly impressed. Um, and now I'm going to try to explain to you what are you seeing in this image? So, to start off with, we have to define what we mean by a black hole. And in order to do that, we have to go back and understand how gravity works. So this little diagram on the right is intended to show you what happens if you launch a spacecraft, a projectile, a satellite, or something, and you want to put it into an orbit that is circular and close in, or you want to put it into an orbit where it goes further away, so you get an elliptical orbit, or you want to actually get it to leave orbit and go off to visit Mars or the moon or something else. What is happening in these orbiting projectiles is that the energy associated with the motion of the satellite is balancing the Earth's gravitational pull. So you give an object motion, and there's a force associated with that. We like to say that mass times acceleration is this force. But at the same time, the gravity of the Earth is pulling back on the orbit, on the object, and not letting it escape. So for a satellite to stay in orbit around the Earth, the gravitational force has to balance the force associated with the motion. And the difference between getting into the circular orbit versus the elliptical orbit is how much force you give it, which is essentially how fast you make it go. And you can calculate what aerospace engineers, when they wanted to put a satellite into a particular orbit, they figure out how much energy they have to give it, how fast do they have to get it to go. And if they do the calculation correctly, then the satellite goes into the right orbit. And if they don't do the calculation correctly, it either falls back onto the Earth, gets into some different orbit, or flies off. So we can, for an object, Nina has a question. Nina?
Yeah, okay. So the Earth travels
Oh,
at a different speed around the sun depending on how close the sun is to the Earth. Is that the same for these satellites that have either a
For,
circular orbit or an elliptical orbit?
for a circular orbit, the speed would be the same. For an elliptical orbit, the satellite travels faster when it's close to the Earth and slower when it's further away. Maybe we'll talk about that one of these days,
Okay.
because that actually is something called Kepler's second law, and it's really important. And one of the things I wanted to talk about, maybe not in February, but maybe in April, is I want to go through the history of how we learned all these things, because some people have said they're interested in history. So stay tuned. Okay, let's say we actually want to send an object out to Mars. We want to send Elon Musk to Mars. In order to do that, we have to give the spacecraft enough velocity so that it can actually escape the Earth's gravitational pull. And we could calculate that velocity. We call it the escape velocity. That's the velocity that you need to give to a satellite in order for it to have enough force associated with its motion so that it can escape the massive object's gravitational field. So now we can define a black hole is an object of any mass, but which is so dense that its gravity will not allow light to escape. And we know that light travels at the speed of light, so it must be that the speed of light is the escape velocity of a black hole. If the escape velocity is equal to the speed of light, then light doesn't travel fast enough to escape from a black hole. So that's our definition of a black hole. So now this is very superficial, but it gets us to the point where we need to be. Maybe we'll talk more about black holes later. Light cannot escape from a black hole. This allows us to make a mental picture of a simple black hole. We don't really know what happens at the center of a black hole. Most of our equations kind of fall apart there, so we call that the singularity. But what we can say is a black hole has a radius. We can calculate the escape velocity for any mass object that has mass and a size. And it's given by this equation where we have a constant in here called the gravitational constant. And the point of this is that the escape velocity of a black hole, which is related to the mass of the object and its size, is equal to the speed of light squared, the speed of light times the speed of light. So, oops, we jumped ahead somehow. We can define something called the Schwarzschild radius of any black hole. It is the radius of that object related to its mass and the speed of light. Again, this is just constant numbers. They don't vary. I can tell you, if you tell me the mass of the black hole, I can tell you how big it is. If you can tell me its size, I can tell you how massive it is. And a black hole is an object of a given mass whose radius is smaller than the Schwarzschild radius, therefore its escape velocity is greater than the speed of light. Okay, now there's another trick about black holes which proves to be very convenient. And that is that black holes are not sitting out there without having things around them.
The names to be changed on official maps and federal communications. The company says it has a long-standing practice of applying name changes when they have been updated in official government changes.
Okay. A black hole, and so here's an artist's rendition. We don't make pictures like this. We have a black hole, so no light can escape, so it looks black. But it may have material around it. What I mean by that is gas and stars. And it turns out that if those gaseous stars come close to the black hole, remember they're moving too. So they don't fall straight in, they're moving too. But they will have a tendency to form what we call an accretion disk around the black hole. And that's what we might be able to see. So again, I'm not going to go into the detail of all of this because it's very complicated, but we have a theory for what we ought to see when we look at a real black hole, in particular, a supermassive black hole having a mass 1,000,000 to billions of times more massive than the sun. These are objects that are much, much more massive than any star we know of. And while the light can't escape from the black hole itself, the idea is that we ought to be able to see material before it falls into the black hole or when it is at least orbiting around the black hole. So our prediction is that we ought to be able to see an object that shows up as black but has glowing material around it. So that is what you are seeing here. You are seeing material around a black hole. Okay, that Martha says that it must be true, right? Let's take a little bit closer view of what you're seeing here and why we believe that this is actually an image of material very close in to a black hole. So the first, and I will tell you that there are now two objects that have been imaged. Now I'm going to show you the pictures of both of them, and they're going to look boring. And I will explain why that is actually the most important result. So we know that there are galaxies in the universe. Here's a Hubble Space Telescope image of a galaxy that's located about 50 million light years from us. It's called Messier 87. It's what's known as a giant elliptical galaxy. It's looks kind of elliptical. It's got a mass that's significantly more massive, like a factor of 1,000 times more massive than the Milky Way galaxy that we live in. And it's been known for a very long time that if you focus in on the very, very tiny inner center of the galaxy and you take a very short exposure, you see what is known as a jet. It is seen in optical light, and it's also seen in radio waves. And in this case, the jet is traced for about 5,000 light years across. Remember, a light year is the distance light travels in a year at 186,000 miles a second. And what we also know is that material is being ejected at very, very high velocities. And it's this object, the bright point, that we're most interested in. The only way we can understand that you can eject material at these high velocities is to have something associated with a supermassive black hole. So now we can say, remember I said that we have this simple model of a black hole, and yes, black holes are more complicated, but this is a pretty good first approximation of a black hole. If I know the size of a black hole, I can tell you how big it is. If I can know, I can know how mass, if I know the mass, I can tell you the size. If I know the size, I can tell you the mass. In fact, the Schwarzschild radius of a black hole changes at a rate of about 3 kilometers per solar mass. So if I took the sun and I squished it down to have a size of 3 kilometers, it would be a black hole. But I'd have to do that. The sun is not a black hole. If I took a mass with the Earth's mass and I made it 9 millimeters across, that would be a black hole. In this case, we're talking about the supermassive black hole in this galaxy, which we are able to measure its mass through other means, and I'll show you how we do that for another galaxy in a minute. We know that it has a mass of about 6.5 billion solar masses. Therefore, the Schwarzschild radius is about 6.5 times 20 astronomical units. And that's a weird unit that astronomers use relative to the solar system. It's about 20 astronomical units is the orbit of the planet Uranus. 1 astronomical unit is the orbit of the Earth around the sun. So I know how big the Schwarzschild radius of the supermassive black hole in M87 might be. And the point is, it's roughly the size of what we see in that image. So here's the optical image with the jet in it, and here's the image of the black hole. And I just want to point out that this is not an image taken by the James Webb Space Telescope, because in order to be able to see that hole, you need an angular resolution of 20 micro arc seconds. And the moon is 3,600 arc seconds. This is much, much smaller than that. And in fact, James Webb has a resolution 3,500 times worse than this image. So you can say, how did we make this image to have be able to see something so tiny? Well, that's why we haven't done this before, and it's why JWST cannot make this image. To make this image, we actually have to use a bunch of radio telescopes that are spread out around the world. And here are a picture of the sum of the telescopes. We call, and nowadays, this was the first image came from these telescopes. We now use as many telescopes as we can possibly get, spread out around the world from Greenland to the South Pole, from Hawaii to Germany and Sweden. And we look at the same part of the sky at the same time. We record the signals received at each of the telescopes, and then we reconstruct the image. And that we're effectively making a telescope as large as the Earth. And we get this image. And I want to show this one because, again, to show the size scale that we're talking about. We said that a 6.5 billion solar mass telescope has a size that's about 6.5 times the size, has a Schwarzschild radius that's about 6.5 times the distance from the Earth to Uranus. So this just shows the sun. Here shows the orbit of Pluto. So we're talking the Schwarzschild radius is actually about this size. We need actually a telescope that is bigger than the Earth if we really want to truly make a good image of the supermassive black hole, but we're getting very close. This is just the location of the Voyager 1 spacecraft, which has actually left the part of the solar system that is occupied by planets. Okay. So now we made one image of a supermassive black hole, and it's not a perfect image. We'd like to do better. There are ways that we in the future will be able to do better. But it's also important for us to try and image other supermassive black holes. And so the other place that's convenient, and I should say that M87 is sort of the biggest black hole close enough to us so that it was, and it's really, really massive, 6.5 billion solar masses. So it was the first supermassive black hole outside the Milky Way galaxy that was targeted by the Event Horizon Telescope. We also know, however, that at the center of our Milky Way galaxy, there is also a supermassive black hole. So this just shows a very panoramic view taken by Hubble in the near infrared. So not at light that our eyes are sensitive to, but light that, say, infrared goggles would be sensitive to. Because at optical wavelengths, we can't see to the galactic center because there's all this dust and gas in between. But we can focus in on the very, very center of the Milky Way, and we know that there's a supermassive black hole there also. Here's our picture of the center of the galaxy. Here's the image that we'll talk about in a minute of the supermassive black hole by the Event Horizon Telescope. This looks very similar to the image that we saw of M87, doesn't it? That's something we're going to talk about. If we actually look at the center of the Milky Way galaxy, there's a lot of hot gas, which is seen in X-rays. So that's what you see. The blue is from the Chandra X-ray Observatory, which is a satellite in orbit. There's also gas that's cool, and then the orange is from stars, which can be viewed if you look with an infrared telescope. Sagittarius A star, which is what we call the supermassive black hole in the center of the Milky Way, is much less massive than the supermassive black hole in M87, so its Schwarzschild radius is much, much smaller, but it's also much, much closer. So it was the other target, but because it's much less massive, it's a much fainter source, and so it took longer and more telescopes for them to be able to get an image of it. Now, the reason that Peter raised his hand.
Sorry, I'm still trying to wrap my head around all of these terms, so forgive me. But for a celestial body to be a black hole, does it have to cross a threshold of density? Is that what really determines a black hole?
That is exactly what determines it. It
Okay.
has to become so dense because it's small and massive that light can't escape.
Got it. Thank you. Okay.
Okay. So here we have a little movie starting in 1995 of observations of stars around a very, very strong radio source, which is called Sagittarius A star. And you are actually watching here from 1995 for about 15 years, and people are continuing to observe it from 1995 to 2020, a 15-year period. Astronomers are able to watch the motions of stars, some of which are orbiting around that object, which is a compact, unresolved point-like radio source. You can also notice that when the stars like this one are far away, they travel slowly. When they come close, they travel faster. And so we are actually able to watch the orbit of these stars around this object. And this observation of this led to Reinhard Genzel and Andrea Ghez to receive the Nobel Prize in physics for using their they use different telescopes, they use different instruments, they made the same observations, and were able to compare them. I can assure you, if they didn't agree, they would say they didn't agree, but they did agree. And they were able to use those orbits to calculate the mass of the supermassive black hole. And because it is so small, it must be a black hole. So let's go back and watch again the orbits. In particular, this object right here, which is known as S02. It has an orbital period of 16 light years. It comes within 17 light hours of the closest approach to the black hole, which means it's traveling at 5,000 kilometers a second. The Earth moves around the sun at 30 kilometers a second. It's in a very elliptical orbit, but knowing the laws of physics and Kepler's third law, which we'll talk about sometime in the future, we can estimate that the mass of this supermassive black hole is 4 million solar masses. Again, M87 is 6.5 billion versus 4 million. But now we could calculate, therefore, astronomers can calculate how big the Schwarzschild radius of that one is. It's much smaller because the mass of the object is smaller. It's much smaller than the size of the Schwarzschild radius of M87, but we know what we have to do in order to make the observation. And so here's the image of Sagittarius A star. The photons that you're seeing are coming from gas particles that are in orbit around the supermassive black hole. It's not a simple ring. There are bright knots that you can see, which maybe people think are the results of magnetic fields, but they're also concerned about them being some artifacts in the imaging. And so people are hoping to continue to watch this to learn more about what they're actually seeing. But I think what's interesting is this image has the sharpness of detail, the quality of an image of a donut taken from the Earth when the donut is on the moon. So you should really be impressed about
Say that again. Say that again.
The image is equivalent in its detail to an image taken from the Earth of a donut on the moon.
So if you extrapolate that out, that's pretty impressive.
Yeah, that is my point.
Got it.
Okay.
Got it.
You should, the image, it doesn't show you the beauty of structure and color that you see when we look at other images of supernovae or planetary nebula, but you should be impressed by it. Okay, so what we think, we have an idea that we're seeing the projection of light from just outside what we call the photon sphere. The photon sphere is where if you have photons, remember, once the escape velocity, because once a photon is far enough away that it doesn't actually get constrained in the black hole, just like a satellite, you can launch a satellite into orbit around the Earth. It doesn't get stuck in the Earth if you give it enough velocity. In this case, if it's far enough away, the photon doesn't get trapped by the black hole. The photon sphere is where photons actually orbit the black hole and maybe they can escape. We call that the photon sphere. We think we're seeing photons here from just outside the black hole. So the Schwarzschild radius is in here. This image is not perfect because we don't have enough angular resolution to be able to make out more details, so it probably looks wider than it actually appears to be. But we understand that what we're seeing here is photons and gas particles which are spiraling into the black hole but haven't gotten there yet. And so that's our idea, but we want to know more. We want to know why we see these different knots. And in fact, there have been a couple now of images made with data taken at different times, and the structure of the knots appears to change a little bit. That's really interesting and something that we don't completely understand.
Martha, can you define event horizon?
Yeah, okay. Event horizon. Here's a way to think about it. How do we know about something? We receive information. In particular, in astronomy, we receive information that travels at the speed of light. Let's say there's an event. How do we know about the event? Let's say we have a satellite and it has a radio beacon on it, and that radio beacon is transmitting every second. If the radio beacon is inside the black hole, we can't receive the radio transmission because the transmission cannot escape from inside the black hole. So if there are events taking place inside the black hole, we cannot know about them. If the radio transmitter is outside the black hole, we can learn about events. So the edge of the black hole, outside of which we can know about events, and inside of which we cannot know about events, is called the event horizon.
Finally, someone's defined that for me, other than the
Yeah.
movie.
Yeah, well, we can talk more about this later
Okay,
sometime. Okay, so here's what the point that I wanted to make. We have the two images superposed. We know that Sagittarius A star has less mass and M87 is bigger. 4 million solar masses, 6.5 billion solar masses. But in fact, superficially, the two images look almost the same. And furthermore, they look pretty much as predicted. I think that's the really important message is we actually understand black holes. Not maybe in detail, but we actually could make a prediction of what image we would expect to see. And we designed telescopes and experiments so that we would be able to make images on the appropriate scales according to our understanding of the size of a black hole for a given mass. We measure the mass again from motions of stars or gas around the supermassive black hole, as we did in the animation that got Getz and Genzel the Nobel Prize. So we know how big the object is, and these objects are the right size. So I think that's what's really exciting. I've shown you the image. I hope I've at least conveyed a little bit about how difficult it was to get these images and how they continue to work by adding more telescopes, which allows them to make better images. It's really, really tough stuff, but they've been able to do it. And the interesting thing to me is that the images, at least to first glance, look exactly as our theory of black holes predicted. That's pretty cool to me. Okay.
I can understand that.
Okay, so now I'm going to show you just finish here by showing you the visualization of a black hole with an accretion disk around it. And this is pretty complicated, but you can go look it up if you Google astronomy picture of the day for the 8th of May of 2024. You'll get to read more and follow up on this visualization. Yeah, there we go. Okay, so you have a black hole with an accretion disk around it, and now you've tipped it over so you're looking at the top. What I haven't really talked about is the fact that gravity in the vicinity of a very massive object, like a supermassive black hole, bends the path of light. We talk about that sometime in the future. And so this visualization is trying to tell us what we should see depending upon the orientation of the accretion disk relative to the black hole. And what we see in the case of our supermassive black holes is in fact something that looks roughly like this. And again,
you have to watch it in here because this battery is dead. That's a brief.
And so you can take a look at this visualization. You can also find lots of other visualizations. We're trying to combine.
Symbol, by the way.
we're trying to combine the observations and our abilities with predictions. Okay, Rena has a question.
Pardon?
It was in the living room, it was reading Bruce and Mark.
Somebody needs to mute themselves. Rima has her hand raised.
Yes. Might it be possible someday to put one of these telescopes, say, on the moon in order to make our Earth telescope larger?
Absolutely. And we would love to do that.
Is it in the plans?
People are talking about it. There are also other ways that you can get better images by going to shorter wavelengths. And so, yes, someday someone will do it. I'm sure. I'm quite sure.
Oh.
Okay, so that's all I had to say for today. We meet next. We decided that for this program we were going to be sometimes at 4 o'clock and sometimes at 7 p.m. What I thought I'd do on the 7 p.m. ones is we'd change it up a little bit, and we'd talk a little bit about the history of astronomy and how astronomers have developed their idea of the universe around us. What is the universe? Today we talked about what is a day and what is noon, and we found out that the answers to those weren't completely obvious. So I think we'll talk more about how our concept of time and how the ancient Greeks in particular figured out the relative sizes of the Earth and the Moon and the Sun, and how they actually figured out that the Earth revolved around the Sun. And we'll also talk in preparation next time about lunar eclipses, because on Friday, March 14th, here in Ithaca, if the clouds obey us, we will actually be able to view a total eclipse of the moon. So that's the plan for February. So does anybody have any questions for me today? Peter again.
No, I was just applauding you.
Oh, okay. Okay.
Thank
Well,
you. Thank you so much. It's great.
Alan has a question. Alan, you're muted.
So that was a great description of this event horizon, these event horizon pictures, and the news that people are maybe even beginning to see traces of a little bit of change in the images. What I've always been wondering is, putting aside the possibility of artifacts, make believe that the artifacts, that's actually a real image. From our general understanding, what kind of time scale would we expect that picture, one of those pictures, to be valid for? Would it be seconds, hours?
No, yeah, it's probably probably you should be able to detect things. You might be able to detect things on scales of months to years. And so that is what. Oops! Why did we get loading my? What I got? Well, forget that. I'm getting my whiteboard loaded. I don't know why that is the case. Something weird has happened. Okay. Now I'm back to normal. And in fact, the time scales that they think they might have seen something on is months to years. It depends on where it depends on the scale size of the variations. And we don't really understand them very much. But if you're in Sagittarius A star in particular, you're working on a scale that's smaller than the orbit of Mercury. And so potentially you can see things on relatively short time scales.
Yeah, some of the gases might be going around at something significant fractions of the speed of light if they're closer.
Yeah, exactly. Um, so what I'll also preview is another time. We've talked about supermassive black holes at the center of galaxies. We also know that we see another kind of black hole, which is a stellar black hole, which are more massive than the sun, but still they're related to stars. And so another time I thought we'd take a look at how we discovered them and what they're teaching us about black holes. But we haven't been able to make any images on the same scale as the supermassive black holes. It's tough stuff. Okay. If it's clear tonight, but it doesn't look like it's going to be, of course, as usual. We did have sun today, though, so we can't complain. But try and look for Orion and Venus and Saturn in the west, Jupiter and Mars up in the evening sky. Otherwise, we'll see you in a month.
Okay, thank you, Martha.
Bye-bye, everyone.
Thank you, Martha.
All right, thank you.